Hello, everyone, and good morning. My name is Scott Doming, and I'm the moderator for today's talk. In addition to that, I'm the engineering manager at the Colorado Laser Division. The Colorado Laser Division is a partner or sister site to today's speaker. And Thorlabs Laser Division as a whole specializes in ultrafast laser technologies from light sources to characterization tools and management devices. Before introducing Dr. Salem, I have a logistical comment regarding the Q&A. We would encourage you to submit questions throughout the talk. There's a Q&A button on the top right of your screen that should allow you to do so. We will wait until the end of the talk, however, to answer those questions. It's now my pleasure to introduce today's speaker, Dr. Reza Salem. Dr. Salem completed his undergraduate degree in electrical engineering at Sharif University of Technology in 2001. He received his PhD degree in electrical engineering from the University of Maryland in 2006, working on nonlinear optical devices for high-speed optical communication systems. During a subsequent postdoc at Cornell University, he continued with that theme, working on nonlinear silicon waveguides and ultrafast optical signal processing. While at Cornell, Dr. Salem co-founded Picoluz with professors Gaeta and Lipson to commercialize time lens technology. He joined Thorlabs as our fiber laser division manager in 2013. And with that, it's my pleasure to turn it over to Dr. Salem.
Thank you very much, Scott, for the introduction, and thank you everyone for tuning in today, listening to our webinar. What I'll be talking about today is the mid-infrared white light laser, and specifically going over design and application of a system like that. What we mean by mid-IR white light laser is basically a broadband source that operates in the mid-infrared part of the spectral optical spectrum. So just to kind of quickly give you an outline for the presentation today, I'll start by introducing what mid-infrared spectral region actually is. So we talk a little bit about the applications of the mid-IR, why such an important part of the spectral part of the spectrum, and we talk a little bit about the applications of broadband mid-IR light sources specifically, and focusing on spectroscopy applications for such broadband light sources. Then I'll introduce sort of the menu of options one has available to them in terms of mid-IR broadband sources. So we talk about different options that are available and how they compare with each other. And that leads us towards the main topic of today's webinar, which is supercontinuum lasers in the mid-IR. So we talk a little bit about what supercontinuum is, principle of operation, different architectures and specifications of a system like that. And that leads us towards specifically looking at the mid-infrared supercontinuum, or what are the building blocks and target specs for a system in the mid-IR region. And with that, we kind of split the talk into two categories. One is building block one, which is the femtosecond pump laser that goes into a system like this. And the second building block would be developing a nonlinear mid-infrared fiber using special soft glass technology that actually gives us the ability to get this mid-infrared supercontinuum. And with that, I will introduce kind of the fully integrated product that we've developed around this technology. And I'll briefly touch on some applications that are enabled by a high brightness source like this. So now kind of moving on to the first topic, which is what is the mid-infrared spectral region and what we mean by mid-infrared in general. For people that may not be necessarily familiar with the terminology for different spectral regions. So what you look at here, this is the wavelength axis, kind of going from 1 micron all the way out to 100 microns. So anything below 750 nanometers or 0.75 micron is considered visible. And the near infrared region kind of starts from 0.75 and it ends around 2.5 microns. So that's the near infrared. A lot of things happen in this region, obviously, that we are all familiar with, including all the telecommunications in the world goes through 1.5 micron bandwidth wavelength region. And then after 2.5 micron all the way out to 25 micron, that's called the mid-infrared region, and there are different definitions of it based on where you would look, but this is kind of the most common way to refer to mid-infrared is 2.5 to 25. And why is this region so important? It's basically the second bullet here, which is that the mid-infrared spectrum really contains very unique and distinct absorption signatures of most molecules that are out there. And a very interesting example of this that came out in the news a few weeks ago was a NASA spacecraft that was able to detect water on the moon by looking at a very distinct absorption line of water at 6 micron. While this is just an example, it's just interesting because it has been kind of a recent and in the big news. But what we really go in terms of what we really see in terms of applications of mid-IR goes way beyond astronomy, and it goes into other fields of industry and other technologies. Specifically, absorption spectroscopy in the mid-IR is used very broadly to detect and identify materials from pharmaceutical industry all the way to environmental sensing. So it has very broad reaching applications. And before I move on, there are two interesting regions within the mid-infrared, which I will touch on a little bit more later. One is called group frequency region, and one is called molecular or fingerprint region. This kind of goes from 2.5 to 7, and then from 7 to 17, as shown on the plot here. And these two are actually very key regions to identify materials. So in terms of applications, one that first I want to talk about is spectroscopy of gases. And here one can determine concentration and also the type of gases that exist within a certain environment. These could be trace gases, and some of those absorption spectra for different gases are shown in the plot here from this reference listed here. And you could see that there are various applications. One is environmental monitoring. For example, there's a big effort in terms of detecting CO2 levels in the atmosphere, and that could benefit from mid-infrared spectroscopy. There are also industrial process control applications where you would try to detect toxic gases, for example, in a semiconductor material processing plant. And then there are also medical diagnostic applications where you would basically look at breath analyzers, for example, detecting diseases through absorption spectroscopy of a human breath. But the applications don't stop at gases. You have a whole host of other applications related to condensed matter, being solids and liquids. And here is where I mentioned earlier, there are two groups of frequencies available. So in the mid-infrared plot, from 2.5 micron to 16 micron, we can identify two regions. One is called group frequency region, which extends from 2.5 to 7 micron approximately. And there's a fingerprint region, which is from 7 to about 16 or 17 micron. What's important about the first region, the group frequency, is that you could actually identify certain functional groups. For example, the CH bond is shown here, having a very distinct absorption at about 3.5 micron. And then the second region, a fingerprint region, actually gives you a unique fingerprint for every molecule. So the first region is used to identify compounds and specific functional groups, and the second region is determined to further narrow down the results of the inspection or detection and determine the molecules very uniquely. So both regions are very important in terms of trying to do interpretation of spectroscopy measurements. So the applications of this really go in a variety of different fields. For example, in food and drug industries, you can look at quality inspection. There are a lot of applications for microscopy of tissue, for example, detecting cancer. These are a little bit more on the research side at the moment, but they're moving into more being applicable in real clinical studies and things like that. So how do we actually do mid-infrared absorption spectroscopy using a broadband source? That's shown here in this little diagram, very simplified diagram. A broadband infrared source is typically paired with what's called a Fourier transform infrared spectrometer, or an FTIR. And what an FTIR is basically an interferometer where it takes the broadband source and interferes the light coming from the broadband source with a delayed copy of itself. And this interference pattern, this interference that's created through this, goes through whatever sample we want to test, and then it goes to a detector. And what comes out of this detector is what's called an interferogram, which there's a whole lot of math about all of this, but what it leads to is that you could take the Fourier transform of the interferogram and recreate the spectrum of the source having gone through the sample under test through taking a Fourier transformation. And what this enables is that you could map out the absorption spectrum of the sample by comparing the spectrum of the source before and after interacting with the sample. And through this, you can actually determine the absorption spectrum over a broad range. And this is why having a broadband source is crucial to this application. This industry, this kind of application of FTIR-based spectroscopy has been around for decades, and it today has a market size more than $1 billion. So this is a very mature and well understood application and industry. But in terms of what we could actually use as a broadband source, that part of the technology has kind of stayed in a decades-old technology, which is the thermal sources. So most FTIR systems that are deployed today use what's called lamps or glow bars. These are thermal sources that the best way to describe them is a light bulb. So an example of that is shown here. So this is basically a glow bar that emits broad range of wavelengths. So it produces a broadband output in the mid-infrared. What's nice about these glow bars and lamps is that they're very compact and very low cost. But the problem with them is actually shown in these two beam profiles here. You could see that the collimated beam coming out of a lamp or a glow bar looks to have a very poor beam quality. So this is not the kind of beam you would expect from a laser, for example. These beams are they have shapes and certain characteristics to them that makes them very difficult to use. So the low brightness aspect of this basically has led a lot of researchers to look for alternatives. And one of the alternatives is synchrotron radiation. And this has been used for research for probably the last decade or so, where you can get much higher brightness compared to a thermal source, probably by a factor of 100, so 2 orders of magnitude, and you can get a spatially coherent beam out of a synchrotron facility. But the problems with this approach is obvious. As you can see in this image here, it's a football field size facility that's very expensive to operate. It's obviously not portable, so experiments will have to go to the facility. So these actually make the use of a system like this very, very limited in terms of absorption spectroscopy applications. And the third option that's somewhat newer, and this is the kind of the most recent technology development, is the supercontinuum. And supercontinuum, I'll go over this a little bit more, is basically a laser system that converts a narrowband pulse into a broadband output. So this is a pulse laser and creates a broadband output by propagating light through a nonlinear waveguide. And again, I will go through the principal operation in the next few slides. But imagine that a system like this that can fit into a box, a benchtop laser, such as what's shown here with the SC4500, which is the product that we're going to kind of dissect and talk about today. This system is very portable and is very compact, and it's much, much cheaper to operate compared to a synchrotron. And on top of that, it can compare or even exceed in terms of brightness with a synchrotron facility beam line. And the beam that comes out of these systems is basically a single mode laser beam, which makes it very attractive for applications that are demanding in terms of beam profile and beam quality. So how do we actually make a supercontinuum? So this is kind of a simple way of describing the process. There is a pump pulse, so there's a pulse laser, which we call the pump laser. and it has a fairly narrow bandwidth. So it could be a directly switched laser diode, or it could be a mode lock laser, variety of options there. And if I put this with enough energy, enough power level into a nonlinear waveguide, so propagate the pulse through this, with the right conditions, you could actually blow up the spectral bandwidth of the source and get a much broader spectrum through what's called supercontinuum generation. So the input being narrow band, the output is broadband, and that's kind of what we're looking for in a broadband source, is having many colors at the output. So, which is why we call it the white light laser, because it basically has all colors. What's interesting, what's the most important aspect of a supercontinuum, or really the selling point of it, is the high brightness. And there are two things that give the source those characteristics. One aspect is the high power. So when we generate a supercontinuum, we have a whole menu of options in terms of what pump laser to use. So if we use a pump laser with high average power, we end up with a source, a broadband source that has a very high power. So that part is somewhat easy to scale in real industrial laser systems. And the second advantage of supercontinuum is the high beam quality. And that really comes from the core of the supercontinuum generation principle, which is that it's generated typically in a single mode waveguide. So that being the nonlinear waveguide. So this, for example, could be an optical fiber. And this propagation in a single mode waveguide basically produces a beam quality that's like a single mode beam and is very pure. So that kind of leads us to another topic with supercontinuum that just like with anything else in nature, there are pros and cons with any sort of process. Here we utilize nonlinearity to broaden the spectrum of a pulse laser. Nonlinearity comes at a cost, which is that it could lead to creation of noise in the output spectrum, because the process is it could be very chaotic depending on how the system is designed. So there's a lot of thought that goes into designing a low noise supercontinuum system. But why is that so important? First of all, in a measurement related to absorption spectroscopy, really the key is the signal to noise ratio. So this is a parameter that determines the measurement sensitivity, and it determines the speed of the measurement. So these are really the most important parameters in a measurement like this. But there are two sources of noise. One is detector noise, which is sort of limited by what's used in our FTIR system in terms of a detector. And the second one is the light source intensity noise. So these two kind of pair together to provide, to basically produce the ultimate signal to noise ratio of the system. And there could be two different regimes. For example, a quiet but low brightness source, like a thermal source, could produce signal to noise ratios that are primarily limited by the detector noise. But on the other side of the spectrum, a very bright but noisy source, like a noisy supercontinuum laser, could produce signal to noise ratios that are actually limited by the laser noise itself, which is also not ideal. So the ideal situation obviously is to produce a light source that can be both bright and quiet, and that's really the challenge. So this topic of nonlinear spectral broadening of a laser through supercontinuum and the noise that rises from that has been studied very extensively by a lot of academics. And as an example of it, I put this image of this book here, Supercontinuum Generation Optical Fibers, by Dr. Dudley and Dr. Taylor. And some of the pioneering work on this was actually done by Dr. Dudley, looking at coherence of supercontinuum. Coherence basically determines the pulse-to-pulse variation of the output spectrum of supercontinuum and how we could make that as stable as possible. So reduce the noise in the output spectrum as much as possible. And there's a lot that goes into that. There's a lot of information that I can't go over today, but the high level conclusions of that study basically says that the key to a system like that is to use a femtosecond pump pulse to start the process. And this typically would be less than 100 femtosecond in pulse width. So this really short pulse width turns out to be the key in terms of producing the shot-to-shot coherence or low noise system. And on top of that, we would also want this process to happen in a short interaction length in the waveguide. So we don't want meters and meters of fiber or waveguide to produce the supercontinuum typically, because that just adds to the chaotic part of the process that gives rise to noise. So we took that kind of guidance in terms of femtosecond architecture, and this was kind of our main design objectives for producing a mid-infrared supercontinuum source. We start by basically saying that the pump source in a system like this would have to operate in the femtosecond regime. So this would give us the low noise performance and the coherence. We also wanted to have a system that's environmentally stable. So we looked at polarization maintaining fiber lasers that are more robust and compact and stable. And we also wanted to have a nonlinear waveguide that has a simple and reproducible fabrication process, and it can be easily integrated with the pump source. And those design objectives led us into these two design objectives. One, with respect to the pump laser, we chose to use a thulium doped fiber laser near 2 micron. And we also looked at entirely a PM fiber design, polarization maintaining for stability. And in terms of the nonlinear fiber design, we focused on step index fibers in the mid-IR, and I will talk about the indium fluoride fiber being the choice that we made. The step index configuration allows a standard fiber draw process, and it also makes the system very compatible with integration with the pump source. And we'll go over this a little more detail, obviously. First, focusing on the pump laser, this is the design of our pump laser. We chose to start from a 1550 nanometer mode-lock fiber laser to get to the 2 micron region. And the reason is that the technology for mode-lock fiber lasers at 1550 is very mature, very stable, and lower cost oscillators are now available from a number of different vendors. And this technology is mature enough that we could build a reliable source, reliable laser around that technology. The 1550 nanometer mode-lock fiber laser goes through a chain of amplification and nonlinear fiber to basically redshift its spectrum out to the 2 micron region. And this is a process that's well understood and used in a variety of different research applications. It's called soliton self-frequency shifting, and through what's called a Raman soliton self-frequency shifting, you could shift the 1550 nanometer light out to 2 micron region. In the case that we are presenting here, we basically get an average power of 25 milliwatts and a repetition rate of 50 megahertz that comes from the mode-lock fiber laser. And we follow that with a what's called a thulium doped fiber amplifier, which is an amplifier that operates in the 2 micron region to basically boost the output power. And here's the output of that. Basically, by designing this properly, we could get more than 500 milliwatt output power. And by also managing dispersion in the amplifier chain, we could get a very short pulse. So this is the intensity autocorrelation of the output pulse that you can look at here. And it shows us a pulse with less than 100 femtoseconds coming out of the thulium doped fiber amplifier. And the spectrum of the output and input of the thulium doped fiber amplifier are also shown here, showing a spectrum centered around 2.1 micron coming out of the TDFA. And then our next challenge here in terms of building the product around this was to kind of package all of this and integrate all of this into one laser system. And that's this product that we call FSL 1950F. It's a fiber coupled output fiber laser that basically integrates what I just explained into one box. What comes out of the laser is 500 milliwatt average power, 50 megahertz, and it's a polarization maintaining fiber, as I mentioned, so it gives a more than 18 dB polarization extinction ratio and a pulse width shorter than 80 femtoseconds. So now the next goal is to take this pump laser and pair it with what we talked about, a nonlinear waveguide to broaden the spectrum. Here's where in-house mid-IR fiber design and manufacturing comes into play. What's shown here, this is actually a real picture of our draw tower in Newton, New Jersey, where we develop our own glass in the mid-infrared region, and we draw our own fibers. And these fibers are specifically designed for mid-infrared applications because they have transmission windows that go past the cutoff for silica fibers, which is typically around 2.3 micron. And there are two types of glasses that are available. One is a zirconium fluoride, which you can see transmits almost out to 4.5 micron. And then one is called indium fluoride, which actually transmits out to 5.5 micron. So based on this and based on our desire to go as far into the mid-infrared as possible, we picked the indium fluoride glass for our design of nonlinear fiber. A little bit more on the fibers. As I mentioned, the glass production is all done in-house, so we have a lot of control in terms of numerical aperture of the fiber, refractive index, and things like that. But also these fibers are made with a very mature draw process that's actually similar in terms of the techniques used to silica fiber draw facilities. So these are draw processes that are very well understood and very mature. And what that gives us is very good control of geometry of the fiber, which, as you will see, it turns out to be really key for nonlinear fiber development that we're looking for. So we're looking for core and cladding diameters that are very accurate, concentricity, meaning that the core should be exactly at the center of the cladding, and also having a numerical aperture that we have control over. And finally, these kind of fibers are, in terms of reliability, they're really tried and true. These are materials that are military certified. They're used in a broad range of applications, and they are very long-term stable and robust in the different environments. So this is another advantage that this technology offers for a supercontinuum laser, which we would have to operate for thousands of hours in a setting, for example, for a spectroscopy application. If you want to learn a little bit more about this topic, interestingly, we had another seminar, another webinar about a month ago by my good colleague, David Gardner, who's our senior process engineer for optical fibers. And he talked a lot more extensively about how these fibers are manufactured and how the glass is developed and all of that. And I really encourage you, if you're interested, to take a look at this webinar, which is recorded and available on our website. Now, moving on to our design for the indium fluoride fiber that we're using. As I mentioned, we're using step index fiber, and what that means is shown in this little cartoon over here. So this is a step index fiber. Basically, it's the simplest form of fiber you can imagine. It's a solid core with one refractive index called core refractive index, and then a cladding that's also a solid cladding around it, which has a cladding refractive index. And the difference between those two indices of refraction basically gives us what's called numerical aperture of the fiber, which is the parameter that turns out to be the key in terms of tuning the dispersion properties of the fiber. So we did some numerical modeling in terms of the chromatic dispersion of the fiber. And the reason why this is so important is that to get efficient supercontinuum generation in the mid-infrared, one would need to, first of all, produce a fiber that has a zero dispersion wavelength close to the pump wavelength, which is 2 micron. And also would have to produce a fiber that has low dispersion in the mid-infrared for efficient spectral broadening. And what you see here in our simulations is basically that we varied the core diameter of the fiber from 5 micron to 9 micron in steps of 1 micron. And you can see that that drastically changes the dispersion profile of the fiber over the wavelength of interest. And these are all done with a fixed numerical aperture of 0.26. But the takeaway message here is that as I change the core size of the fiber, I can tune the zero dispersion wavelength of the fiber from where the material zero dispersion wavelength is around 1.6 all the way out to 2 micron. And that really is the key to produce an efficient supercontinuum. And the solution turns out to be around 7 micron based on our simulations. So we took that and we tried to build that fiber in a real draw process. So we have drawn the step index supercontinuum fiber with an NA or numerical aperture of 0.26. After the draw, we measured the core size of the fiber, and it turned out to be between 6.9 and 7 microns, so very close to the target. Cladding diameter of the fiber was right on target at 125 micron, which makes it compatible with standard fiber claddings. And we also get a transmission window out to 5.5 micron. So this is a fiber that sort of met all of the specifications that we were hoping to get. And then we took the real properties of the fiber after the measurements in the lab, and we plugged them into our own numerical simulation for supercontinuum generation. So what you're looking at here in this sort of colorful plot here is what's called the evolution of supercontinuum. On the vertical axis, you see distance propagation in the fiber, which ranges from 0 to 60 centimeters. And on the horizontal axis, you're looking at the wavelength. And you notice that we start around 2.1 micron with the pump that comes from that thulium doped fiber laser. And very quickly, within a few centimeters, we can broaden the spectrum all the way out to 4.5 micron. So this supercontinuum in the fiber that we have designed, at least in theory, seem to work very well. And we believe that an optimal length for a system like for a supercontinuum fiber like this would be somewhere less than 20 centimeters, even as short as 10 centimeters. So we took that simulation and we tried to prove that is actually true in experiments. So here's our initial experimental setup when we started doing proof of concept. We took our FSL 1950 fiber laser at 2 micron. We coupled it into the indium fluoride that was fabricated at a length about 15 centimeters. And we used collimator pairs, basically aspheric collimators, to couple from one fiber into another. And the output of the fiber we collimated using a reflective collimator, which has a very broad operating bandwidth. And we coupled that after some attenuation into our own Fourier transform optical spectrum analyzer, which is OSA 205C, also made by Thorlabs. And this OSA can cover from 1 micron all the way out to 5.6 micron, which basically matches the spectral region of interest for our application. The coupling efficiency we got through this was about 70%. We got an output power of 350 milliwatts. And we measured the output spectrum, and this is what we observed, basically a supercontinuum extending from 1.3 micron all the way out to about 4.6 micron. And this very closely was in agreement with our simulations that I mentioned before. To take this one step further, we looked at integrating the fluoride fiber with the pump laser. Really, the challenge here is to try to replace the free space coupling setup with the 2 collimator pair that I mentioned with a more robust and compact and more efficient splice between 2 fibers. But joining the 2 fibers together is challenging because fluoride fiber and silica fiber are about 5 times different in terms of their melting points. So the glasses actually melt at completely different temperatures. And to do this, we would need a very tight control on glass melting properties. And what we used was Vitrans GPX 3400, which is an automated glass processor. And it can give you the controls that you'd need in terms of the melting conditions of the 2 glasses to be able to join them together in a controlled and efficient way. So we developed that using this Vitrans system shown here, and that recipe and that technology has led to very repeatable coupling efficiencies out to about 80% or better. And we also designed our own packaging solution to put the splice into some kind of protective housing that can withstand long-term reliability testing. And that package is shown here. So basically, we come from the pump laser into a silica fiber. There's a splice inside of the package that joins it with the fluoride fiber. And the output of the fluoride fiber is just simply terminated in a FCAPC connector, and it gets plugged into the collimator that collimates the output light. So all of that goes into what we call SC4500, which is our fully integrated mid-infrared supercontinuum system. So this system basically takes the FSL 1950F 2-micron fiber laser, adds on this splice module and collimation optics, and it provides a collimated output beam with all these colors from 1.3 micron to 4.5 microns. So a white light mid-infrared laser. The minimum output power is about 300 milliwatts. Repetition rate is 50 megahertz, and the output has a single mode collimated beam with a standard size of 5.5 micron. What's also important about the laser that we kind of started looking at this femtosecond architecture to get low intensity noise. So we wanted to really characterize that and look at it more carefully. We did a lot of careful noise measurements on this system, and we measured relative intensity noise, which for the frequency contents between 10 hertz and 1 megahertz was measured to have less than 0.03% relative intensity noise. And this is a noise level that is remarkably low for a supercontinuum system, and we believe that this is really entirely the result of the femtosecond architecture that's used. So talking a little bit about applications. First, I will show a simple application that we demonstrated at one of our trade shows about a year ago. And this is just to kind of demonstrate we could do absorption spectroscopy using the SC4500, particularly if we pair it with our own FTIR spectrometer, the OSA 205C, which is basically a spectrum analyzer version of an FTIR. What we did was that we used what's called attenuated total reflection setup. And this is a very standard technique used in spectroscopy applications, where you would put a prism on the beam path and you reflect light off of a prism through total internal reflection. And what happens is that there's what's called a tunneling effect or evanescent field that leaks through above the prism where the light is reflecting. And at that interface, there is some light matter interaction that can happen over a very short interaction length. So if you put a sample on top of the prism, you can actually see some light matter interaction as the light bounces off the prism. And this technique can be used to measure absorption spectra, specifically for samples that are highly absorptive. So we can't use a thick sample. We need a really short interaction length. Some examples that we did in our trade show exhibit demonstration was oil and isopropyl alcohol. And here I've shown some of the data that we took from that just to show you what level of accuracy we can get with a system like this. So here what you're looking at, the red plot and the blue plot are almost overlapping entirely, except for a very tiny region around 3.5 micron. The blue spectrum is the background supercontinuum laser output, so that's before placing the sample. And the red curve is after placing an oil sample on top of the prism. So we get a small amount of absorption from the oil that's placed on top of the ATR prism. And if I subtract the two, and if I have enough signal to noise ratio, I can get a clear picture of what that absorption signature from oil is. And that's what we did, and that's the plot here. You could see that this very clear with high signal to noise ratio absorption signature can be measured for the oil that was used in this experiment, and that clearly matches what's called the CH bond in those functional groups that I talked about before. So this is a very well-known signature for oil, and can be measured with high signal to noise ratio using a system like this. But kind of thinking a little bit more broadly in terms of concluding our webinar today, I want to talk a little bit about what kind of applications this actually enables. kind of looking at what's out there and what can benefit from a really high brightness, high beam quality laser like this. One application is what's called open path analyzer. If you look at a lot of the applications that are looking that are trying to detect gases, one of them is when we do remote sensing of gases. So we would have like a telescope with a broadband light source, and this goes through atmosphere or any kind of gas sample that's on its path, and it transmits light over hundreds of meters in most cases, or tens of meters, and it reflects back from a large retroreflector and comes back into the telescope, and through FTIR people can detect the absorption signatures of gases and determine the type of gas and concentration of it for a variety of different applications. It could be environmental monitoring, industrial plants, hazardous materials, or even chemical agents for some defense applications. And these open path analyzers are commercialized, they exist, they all use thermal sources as a source of broadband radiation. The main problem with thermal sources is that they have a limited range of operation due to the fact that no matter how many optical instruments we put in front of the beam and how we design it, there's going to be a limit in terms of the divergence of the beam, just because the beam quality is not good to start with. So this limited divergence and this rapidly diverging beam leads to limits in terms of the range that you can achieve with a system like this to get a reasonable signal-to-noise ratio. Now, supercontinuum laser, in contrast, I've shown this is the beam profile coming out of the SC4500, and you can see that it has a circularity better than 97% and an M-score of 1.1. So these are properties of a very well-behaved circular single-mode beam. And what you can get with this is that by properly designing a beam expander or some kind of telescope, you could actually transport this beam over much longer distances. Just as an example, if you have a 5 centimeter diameter ideal Gaussian beam, you get a divergence of 40 microradians, which means that the beam size will only double after a kilometer of propagation. So these kind of systems can actually be designed much better using a source with high beam quality. The second application is sort of looking at the reverse of this long path analyzer. Now looking more at microscopy applications. And this system, these images are from the reference that I've pointed out down here on the bottom of the slide. But this shows a representative of the type of measurements that has been done by a lot of different researchers. So a broadband source of radiation going into an FTIR system can also be coupled to a microscopy system to basically measure the absorption signature of a sample pixel by pixel. So essentially the goal would be to create what's called the hyperspectral image of the sample. So it would be a two-dimensional image that each pixel in this two-dimensional image has a absorption spectrum attached to it, which basically tells the researchers what kind of makeup that material at that pixel has. So you can map out the makeup of a cell or a biological sample or anything that you're putting in this microscope in a two-dimensional image, which could be very useful for example, detecting diseases such as cancer. So the limits for a thermal light source in this application are somewhat obvious. One of them is that just the low brightness level from the glow bar or a thermal source will lead into low signal to noise ratio, which then leads to much slower integration, much slower acquisition, because you would have to use longer integration times to improve the signal to noise ratio. So in an imaging application, this could lead to very long measurement times. And the second problem with the poor beam quality of the glow bar or thermal source is that the resolution is actually limited to about 10 times the diffraction limit. So the diffraction limit, let's say at 3 micron, would be about 3 micron. But with a glow bar, it would be more like 30 micron. So 10 times worse, so in tens of microns neighborhood. And a supercontinuum laser can solve both of those problems, basically offering more power, so measurements can be done faster, and also it can provide much better beam quality, leading to better resolution. And finally, the last application I want to mention is using the same configuration with the microscopy and FTIR system, but now add another element, which would be adding what's called the atomic force microscopy cantilever, which basically is a field enhancement technique that would enhance the electric field at the tip of this AFM cantilever, which would, this enhancement essentially localizes electric field such that you could beat the diffraction limit and actually get images down to nanometer resolution scale. And this is a very well-known and well-developed technique. A lot of people have researched it. There are companies that offer systems like this. But what really this system needs is a laser beam that can very effectively and efficiently focus its radiation onto the tip of the AFM tip. And so the system can only really be efficient and provide meaningful data if you have a laser-like beam, like a supercontinuum laser. Doing this with a broadband thermal source would just have wasted energy that would then reduce the overall efficiency of the system. So this is yet another application where this good beam quality of the laser could benefit the application. So to summarize, we talked a little bit today about broadband mid-IR sources paired with FTIRs for absorption spectroscopy and where they can be used for identifying materials. We compared the traditional solution for broadband light emission, being lamps and glow bars, with other options, and we talked about the limited brightness of the traditional solution and how we can get around that. For example, synchrotron facilities have provided some relief on that front and providing much better beams and much better brightness levels. But what really can bring this into a real application side of things is what's called a supercontinuum laser, because it's a lot more portable, compact, and lower cost. So this can actually really improve on some important metrics in spectroscopy systems by offering high brightness outputs. We talked a little bit about noise properties of supercontinuum and why this coherence is important and femtosecond architecture is important. And I talked about the building blocks of our system, our femtosecond pumping architecture, and our in-house fluoride fiber fabrication. And we talked about how we fully integrate that all together. And some of the key applications we discussed that could be enabled with a source like this, including remote sensing and some of the microscopy and near-field imaging applications. And before I finish, I just want to acknowledge our team. Our team was really split between two groups. Our laser division team that I work for worked on system design, development, and manufacturing of the overall system. But we also worked really closely, as I mentioned, with our fluoride fiber team, who have worked on designing, developing, and manufacturing of the soft glass mid-IR fiber that I talked about. So I listed some of their names here, and I thank them for all the work that they did that led to developing this interesting product. With that, I'll conclude the talk, and I look forward to answering any questions.
All right, thank you, Reza. I'll start kind of tossing questions out to you that have been kind of collated over the course of this talk. I'd like to thank the audience for supplying such good questions. So the first question, Reza, and I'm going to paraphrase as best I can, basically is a question that we're using a single mode fiber to broaden all these, to make the supercontinuum generated. How can we propagate this octave of color through a single mode fiber that has kind of these cutoffs and things like that?
Yeah, that's a really good question. So this actually happens in pretty much any supercontinuum system. Your waveguide is going to be have to be single mode at the pump wavelength. So we guarantee that the waveguide is single mode at the pump wavelength. But obviously, all these colors that start propagating, some of them may not be fully supported by just one mode, so it might actually excite higher order modes. What we would get in this case, all the infrared wavelengths, so wavelengths that are longer than the pump wavelength, are propagating single mode because they're longer than the cutoff. And the shorter wavelengths could actually introduce some higher order modes. In practice, what we measure, we don't see much excitement of higher order modes, even at the shorter wavelengths. And we believe that this could be partially due to the fact that the fiber is so short and it's basically a very short waveguide. So to answer your question, we are confident that everything in the mid-IR part of the spectrum is fully single mode because of the cutoff being right below the pump wavelength.
Thank you. So in kind of the same vein, can you maybe talk a little bit about how you had the plot showing different core sizes and how it affected dispersion? At some point, though, won't it stop being single mode?
Yes. So as you tune the dispersion, as you tune the core size, obviously that changes the dispersion of the fiber at different wavelengths. And what we're calculating here is the dispersion of the fundamental mode only. So all the dispersion plots that you saw were only calculated for the fundamental mode, which is what we believe we're exciting in the fiber. So all the supercontinuum that's generated is basically generated through the fundamental mode propagation.
Thank you. And so then we actually had a couple questions that I'm kind of joining. How are we doing FTIR spectroscopy, but with a pulsed source?
Yeah, that's a good question. So actually, this is a key point in terms of compatibility of pulse lasers and FTIR systems. FTIRs, they do this interferogram measurement, as we talked about. And that interferogram measurement has a certain acquisition time and certain point by point. So each 2 points in the interferogram are separated by a certain time interval. And if that time interval is comparable to the repetition period of the pulse, then you will start seeing some artifacts in the measurements. The advantage of our system is that we operate at such a high repetition rate, around 50 megahertz, that all of that gets washed out. So the interferogram and the interferometer in an FTIR system basically sees the source as a continuous wave source due to the high repetition rate, because the pulses are arriving much faster in the acquisition. If you start going to kilohertz regime, so going from megahertz, 3 orders of magnitude, down to tens of kilohertz, then in most FTIR systems, you would start seeing some artifacts, which could then really cause problems for doing interpretation of the results. So that is a really key point in terms of compatibility when it comes to repetition rate of the laser.
So now I have a question that's a little more specific to, say, the SE4500. How stable is the output spectrum in time? You know, over a given chunk of bandwidth that's way out in the mid-infrared, what does that look like in time in terms of fluctuations? Yeah,
so we've done various levels of testing in terms of power stability. So I talked a little bit about the short-term noise, which was that 0.03% between 10 hertz and megahertz. But in terms of what we call stability, which is a slower time scale, we've done measurements that basically show in a normal lab environment that power in the mid-IR, if you look at one certain point in the spectrum, is within plus and minus 1%. And that's usually what we look at in terms of pass failing our system. So we would get plus or minus 1% variation in terms of power. So if you filtered part of the spectrum and looked at the power meter, that's the kind of fluctuation you will see over time. And it typically correlates with environment temperature, because that would obviously change certain properties in the laser system.
Okay. Now kind of going backwards to kind of the nonlinear mechanism a little bit. So this laser, or these fibers and technologies you've been discussing, is specific, or at least in this case, specific to mid-infrared light. Can you do something similar to access deep ultraviolet or visible continuum sources?
Yeah, absolutely. I mean, the fluoride fiber technology has also been demonstrated to operate pretty well in the short wavelength side of the spectrum. I think this, particularly the zirconium fluoride glass, has good transmission down in the UV. What you would have to then work on is a different pump laser. So at 2 micron, it becomes challenging to go all the way down to UV, because then you're looking at several octaves of bandwidth in terms of generation of the supercontinuum. But people have actually done work with a 1 micron femtosecond-pulse laser in a fluoride fiber to be able to get down to the UV region. So those things can all be done, and it will require a different design of the fiber. It will also require a new design of the pump source.
Okay. Another kind of specific question to your laser system. What does the stability of the M² look like in time?
We haven't really tried to map that out. I don't expect the M² to change over time. And the reason for that would be that essentially the light is guided in a single mode propagation in the waveguide or in the fiber, and the fiber output is fixed. And the combination of those basically means that the beam is not going to be fluctuating over time. But that's not something that we have extensively studied or tried to actually map out. But I don't expect any variations over time.
Okay. Now a bit of a question that's kind of a technological specificity question. So we're using indium fluoride fibers to make this continuum. Well, why did I didn't see photonic crystal fibers anywhere in here. Why aren't we using PCFs or hollow core waveguides?
Yeah, that's a great point. It turns out, and this is, obviously beyond a couple of minute Q&A session, but I'll touch on it really quickly. In the silica world, people try to shift the zero dispersion wavelength of silica down to shorter wavelengths, let's say to 800 nanometers, to produce supercontinuum. And in that case, it turns out this photonic crystal structure is actually key to shift the zero dispersion wavelength of the fiber down to shorter wavelengths. And those were actually some of the very early supercontinuum experiments in the world, where people used photonic crystal fibers or tapered fibers and did everything at the 800 nanometer region. In this case, we have sort of an opposite problem. We're trying to shift up the zero dispersion wavelength from 1.6 to 2 micron. And we looked at photonic crystal architectures, and it turns out they don't help. So they actually shift the dispersion in the opposite direction. At least the simpler designs that we looked at, there might be something exotic that can do it differently. But it turns out the step index configuration is the better way to get there. And on top of that is more manufacturable. It's much easier to build.
All right, and I believe this might be the last question, and this is a bit of a pro-cons question. How does this sort of system compare to mid-infrared QCLs?
Yeah, so I would say that these systems are a little bit difficult to compare, because QCLs are laser systems that typically operate over a narrow bandwidth. People can tune them using like an external cavity configuration. So a tunable laser and a broadband source are fundamentally different in the sense that a tunable laser provides a high amount of power spectral density point by point, but it will have to be tuned over a certain course of time to sample different points. A broadband laser, like a supercontinuum, can emit all colors at the same time. So while the power spectral density is lower than a single wavelength laser, but provides all these colors at the same time simultaneously. So that's really the one difference. The second difference is that Supercontinuums are much broader than any tuning range that a laser can ever achieve. We're talking about 2 octaves of bandwidth in the supercontinuum, whereas typically a QCL that's tunable would be about 10% of its center wavelength tunable. So that's the second difference. And also, QCLs tend to operate a little bit at a longer wavelength than where SC4500 works, more above 4.5 micron. And the supercontinuum that we've developed, that we talked about today, is in a shorter wavelengths between 2.5 and 4.5, part of the mid-IR.
Wonderful. Well, thank you so much for putting this together. And on behalf of the audience now, I'd like to thank you for a wonderful talk and kind of digging into the details of your technology and the related kind of measurement systems.